All right, math and beats. Welcome back. Follow up on the last video lesson. We're going to show a couple of examples of applications of linear functions. Of course, this is only a very limited number of examples in the vast scheme of all linear functions out there. But let's just take a look at a couple of examples of some applications so we can have an idea of how to proceed on other types of applications. Let's go. Here we go. Here is the first situation, first example. We're going to look at two examples in this video. Here we go. We got Jenny and Carla. They decide to help with a fundraiser at the high school which they attend. So to help, they each bake some delicious chocolate chip cookies and sell them after school in their neighborhood. On Tuesday, they sold 15 cookies and they collected $37.50 off those cookies. And then on Thursday, they sold 22 cookies and they got $55 from that. So they're out there just strolling through the neighborhood, selling cookies and getting money for a good cause. First part of this problem, here we go. Here's the linear function stuff. Find a linear function, let's call it c of x right here. And this function is going to give us the total amount of money that is earned from selling x numbers of cookies per day. So we could think of the total amount of money here that's earned from selling those cookies. That's our output c, and our input the number of cookies that they sell in that particular day. All right, so what do we got to do if we're being told that this thing is indeed a linear function that models this? Then we know that our function, let's call it y is c of x here, is going to be our slope times our input value x plus some number b, which is the vertical location of its y-intercept on the graph. So what do we got to do? Well, we got to find those values of m and b. And recall, m, of course, is the slope, and it is the change in the output direction over the change in the input direction. That's our slope here. Now our outputs, we're calling them y's, but it's also the value of the amount of money that they earned on that particular day. And notice that in the information that we're given in the problem, we have two ordered pairs given to us. In particular, we have an ordered pair given right here, which is, if you sell 15 cookies, they get $37.50. So that would be the ordered pair, input value 15 cookies, output value 37.5, which represents $37.50. We also got another ordered pair here. Notice we got the 12 cookies, and it kind of follows on to the next sentence. They got $55. Well, that would mean the input value 22 is given the output value of 55. So we could think of the first ordered pair here as our x1 comma y1, the first point that we're given, and then the second order pair is our x2, y2. Doesn't matter which one you call which, as long as you're consistent. So now we're able to compute the slope, which we need to find the formula for this function. And that's going to be, all right, y2 minus y1, change in the output, 55 minus 37.5 in the numerator. And note that that is in units of dollars. And then divide that by the x2, which is 22, minus the x1, which is 15. And notice that is the amount of cookies. Cookies. So what do we get from that? Well, we compute. Numerator there is the same as 17.5. And 22 minus 15 is 7, keeping in mind the units, of course. And if you simplify that, you get 2.5, which is a fraction, is 5/2. So again, that's in terms of dollars per cookies. then we got our slope. That's part of the puzzle that we need. Now, notice, once we get the slope, we still need to find that value of b to complete our formula. So to do that, remember our point-slope form, point-slope form of a line is y minus y1 is equal to m times x minus x1, where x1 comma y1 is any point that we know on the graph of this line. So we'll just pick whatever one we want. How about let's pick the ordered pair. Let's do 2255 since there's no decimals. So let's use 22 comma 55 and we'll plug it in. What do we get? Y minus the output, 55, is the slope, 5/2, times x minus that input value, 22. Now, if you multiply out the right-hand side, that's the same thing as saying 5/2 x minus, notice 22 over 2 is 11 times 5 is 55. And then if I simply add 55 to both sides of that equation, I get my function formula. C of x is equal to y is 5/2 x. So there we go. They got the formula now. So if they sell X cookies in some particular day, then we're going to multiply that by 5/2, giving us the total amount of money that they made. And try to think about that conceptually. What that means is that, oh, really that's just telling us they're selling each cookie for $2.50. Hustling. We got it. We got the formula. So then the question is how much money they're going to earn if they sell 67 cookies. So how much money are they going to earn if they sell 67 cookies? We're just going to plug 67 into our function that we got in part A. C of 67 is the same as 5/2 times 67. Press some buttons, doop-a-doop-a-doo, and what you get is $167.50. So they got a lot of money on that day if they sold 67 cookies, I guess, at least for their school. And then finally, we know in part C here that in one day they earned $192.50 by selling cookies. And the question is, how many cookies did they sell that day? So notice this is an output value here, right? This is some C value. And we want to figure out what the unknown input is, X, which is the number of cookies sold, is going to be. So hence, we should set C of X equal to $192.50. And of course, the formula for C of X is 5/2 times X. And we want to know what that X value is. How many cookies did this sell? So we're going to solve that equation. And that requires us to multiply both sides of the equation by 2/5. So hence, X is going to be 2/5 times that $192.50. Now keep in mind here, the units, when you do this, you get 77, and the output here in this situation, should I say the input value, 77 cookies. So, if they sell 77 cookies, they're going to get $192.50. Not bad. So there's one little quick example. Nothing too fancy, but of course you can see that we can make up situations that are relevant to the real world. Let's look at one more example. Let's say that this person, Maurice, they drove to visit a friend at a college in another state. Now his speedometer happened to be broken, but the odometer was still working. And he kept track of how many miles he traveled each hour. This table right here that we see gives us some of those values of data that he tracked along this trip. You see in the first column right here, the time traveled in hours, assuming since he started driving. And then the outputs, think of this as y is the amount of distance traveled in miles. So these at various times, how far he was on his trip. It says find an equation of a function that models the situation. And they say, well, no one told us in this situation whether or not we should be looking for a linear function. And of course, there's lots of different functions out there. So is it really linear? Well, let's check. In order for a function to be linear, remember, call it y is mx plus b. The key thing here is the slope. For a linear function, slope is constant. It never changes. It's always this number m, right? Our rise over our run, our change in our output divided by our change in our input. So slope is constant for linear functions. So really the question is, well, is this function linear that we're looking for that models this data? We'll have to check. And we'll look at the various slopes across consecutive ordered pairs here. Notice, for this first one, the change in the output in the y direction, 34 minus 0, change in the input is 0.5, that's 68. So we got to check if the next ordered pair is also that same number. Take the change in those outputs, 136 minus 34. The change in the inputs there, notice it's 2 minus 0.5. So that's a 1.5. And when you press the buttons, you indeed get the same number. Now, is that enough? No, we need them all to be the same. So let's do a couple more here. All right, change in the next outputs, 170 minus 136. That looks like a plus 136, doesn't it? Minus 136 over 2.5 minus 2, which is 0.5. Again, this is 68. And then finally, changing the outputs of the last two, 272 minus 170 over 4 minus 2.5 is 1.5. Press the buttons, you indeed get 68. So as we can see, the slope here is constant. Now, we don't have a crazy amount of data points, but we have enough in this problem to be confident that, oh, yeah, the slope is constant. This should be a linear function. So we're going to find a linear function that models this situation. Now, notice this order pair right above that is circled in the table, 0, 0. That tells us that our b value in our formula, y is mx plus b, right, tells us that b is 0. Because the 0, 0 is on the table, and hence when x is 0, y is 0. So b's got to be 0. Now we'll use any other ordered pair we like to plug in to get our slope, or just notice we already actually computed the slope over here, right? That 68 is our m value, our slope. So in this situation, y is going to be 68x. So Maurice traveling basically 68 miles per hour here. Now that we know that, let's figure out the distance that Maurice traveled during the first 5.5 hours. Notice that 5.5 is not on this table, so we don't know what it is yet. And so using our formula right here, keeping note that y is in terms of, remember, distance traveled, miles, and x is time in hours that has passed. Then what we're going to do is replace x with 5.5. So what we get is the distance traveled will be equal to 68 times 5.5. Press buttons, 374 miles in 5.5 hours. Now, I know in both of these examples, our y-intercepts went through the origin, but of course, not all linear functions do that. But the procedure is still the same, right? Keeping in mind, we got to find slope. We got to find a y-intercept. using point slope form if necessary. And that's true when finding the equation of all linear functions. Key to some of these applications is picking out the important information from what we're given to create those ordered pairs, which we find the slope from, and use the point slope form to find the formula from. And of course, if we're given some table of values that represents the situation, and if you're checking if the function is linear, you got to make sure the slope is constant. So in the next video, we will talk about more about this constant slope and how it relates to situations in which we don't have constant slope and how we can use that in relationship to the concept of an average rate of change. But for this video, it's over. So, until the next video, Math and Beats, I'm out.